Alright guys, does somebody mind just shutting that door real quick? Alright, so today's just going to be a review. I don't know how many people saw my email to the group. Let me open that real quick before anything. I saw I got 12 responses so far, so that's enough for me to be willing to do it. Basically, I sent this message to the group last night, 2 nights ago. I don't remember. March 5th. Basically, tomorrow night, I would like to open up, you see these classrooms connect? I might come and just open up a few classrooms like in a row and just let whoever wants to come study here. And I'll just sit up here and wait to see if anybody has questions about anything while you're studying. I can't get here until 8 o'clock p.m. So I said that I would start it at 8 and then maybe stay till like midnight. And then I put this little Google form link here for people to respond. And it seems like some people are interested in coming, so I'm going to go ahead and do that. I'll be here at 8 o'clock and I'll open up. How many of you guys think you're going to come to that? Okay, yeah, that's totally cool. So yeah, basically I'm just going to sit up here and you guys can study groups solo. If you want to go somewhere quiet, I can open another room for you, and then I'll just sit here and wait and see if you guys have questions. I can work problems on the whiteboard. I'm not going to record anything, so it's just going to be like a very lighthearted study session the night before the exam. And like if you don't come, like I'm not going to reveal anything that I didn't reveal in class or anything crazy like that, so don't feel like you're missing some secret meeting. But just if you think it'll benefit you, then definitely come for that. That's about all I have there. Did anybody come prepared with any specific question before I sit and just go through this list that we have here? Nothing? All this stuff. This list. For those of you who maybe weren't here last time, oh sorry, what's up? Yeah, for people who weren't here last time or didn't hear me go over kind of the format of the exam, you have an hour and 15 minutes to take the exam. It's like a normal class session. It's worth of time, and it's going to be 6 problems that are going to be similar to quiz problems. So it's basically like trying to take 6 quizzes in an hour and 15 minutes, which I think is plenty of time. I give you guys 15 minutes to do the quiz, but most people finish them in 5 to 10 minutes anyways. So if you've studied, I don't think it'll be very challenging time-wise. I'm not putting anything crazy on there. I mean, obviously I'm not giving identical problems because I want to challenge that you've actually learned the material, but it's not going to be anything that is unfair or that you haven't seen before, or at least that you haven't seen something very similar to. It might be like some mesh problem that I put on the homework and then I swap the current source with the voltage source or something, and it's the same problem, but now you have to just make different equations for it, right? It's nothing that should scare you. You should see it and be like, oh, I've seen this before. Like, I feel comfortable solving these problems. So yeah, with that, what was your question?
I just had like a clarification. Like for like power, since power is like voltage times current, but
yeah,
voltage is like the voltage difference across the resistor, right?
That's right. Yeah, and then obviously there's the other, you can use voltage times current, or you can use the other 2 variations of that equation. But yeah, it's the voltage across the resistor that you're concerned with. Yeah, regarding that last quiz, significant number of you guys didn't read the instructions, it seems like. Let me pull that quiz up. Maybe, I don't know if everybody got their quizzes back yet, but there's a problem like this on the midterm, so I want to address it. Where's my crap? So it says determine the voltages labeled in the circuit below. I think probably half of you stopped right there and just didn't read the rest of the question. Does that speak to a good number of you guys?
Correct. Yes.
So then I asked, do R2 and R3 dissipate the same amount of power? Show your power calculations to support your answer. Yeah, so a good number, you just didn't even attempt that part, which makes me think you didn't read it because it's not that challenging. Did anybody need me to solve that, or is it just that you didn't read it?
Didn't read it.
Didn't read it.
All right.
Yeah, I found out about that as soon as I walked out of class. They were like, "Oh, did you get the power?" And I'm like, "There was a power."
Yeah, guys, look. Make sure to fall. This has been on every quiz. Every quiz all semester. What happened?
She said she didn't even read that.
Like, damn, I didn't read that part.
So I need a.
Used to having the question be in the first sentence, and the second sentence just being stuff we don't really need.
The second sentence is show your work.
I think you're probably used to me just having one sentence in the question. I don't usually ask for anything else. Or it says verify your work with LT Spice on homework, so maybe you're just thinking that that's what it said, even though there's no way. There's no, yeah. I don't know. But definitely on the midterm, make sure you read the instructions. I'm not tricking, like this isn't a trick question, obviously, but just read all the instructions, because if I say, for example, I think on one of the equation or one of the questions I asked you to determine the voltage at this node, and then I said using that voltage determine the current through R5 or something. If you don't determine that current, you're going to lose points. Like that's part of the question. So just read the instructions. It doesn't take that long. Okay. All right. So nothing. You guys just want me to go through this list? Yeah.
We actually see that's problem solved quiz.
Quiz 9? Yeah.
I think that's what they would do for hours.
Yeah, that's good. So this is going to be, get out of there. Let's go look at it. Three K, 2K, 2K, 1K. All right. Okay, so first thing I guess I asked was to solve all the voltages, so that's the first thing I would do. So right off the bat, VS is what? Okay, and then we have a little voltage divider right here, right, with the 3K and the 2K, so I could say VI is going to be my 5 volts times 2K over 5K, or 2/5 of 5 volts, which is 2 volts, right? Any problems so far with that? Good? Okay, and so now what I need to do is the dependent part of the circuit, right? This is a, I guess it would be a voltage controlled current source, VCCS. So it's it's going to take the voltage difference across that resistor, and it's going to take that in as its baseline, and then it's going to multiply by the gain and give us some current, right? So I have 2 volts at the plus side, and then the minus side is at 0 volts. So the current, right, the current of this source is going to be 2 times whatever this gain factor is. So I'll just call it I of my source is 2 times 1 times 10 to the minus 3, or 2 milliamps. Alright, so now let me change colors. I've got a current of 2 milliamps flowing in this circuit, right? So if I know I have 2 milliamps flowing across this 1K, that means that I have a voltage drop of 2 volts, which makes VO 2 volts. Any questions about anything I've done so far? Anybody?
Where did you get that one from, James?
What one?
Current S equals 2 and 1.
This one?
Yeah, to the 1.
That one. I'm just multiplying the voltage input by this gain factor, and the gain factor is 1 times 10 to the minus 3. Alright, so now that I've got VO, I know that the drop across this resistor will be 2 milliamps, right, times 2K, or 4 volts. And so if I go up 4 volts from 2 volts, then I get that VF is equal to 6 volts. Right? So now I've got all 4 voltages. And then, what did I ask? The power. I asked for something about the power. Do R2 and R3 dissipate the same amount of power? Show your power calculations. Okay, so this is R3 and this is R2. Okay, let me just... go back and change colors again. So this is R3 right here, and this is R2 right here. Alright, so the power, right? The power dissipated by R2, if I just look at R2 by itself, it's 2K. It's got 2 volts here and it's got 0 volts here. And the current flowing through it is 1 milliamp in that case. So the power dissipated is going to be the voltage across it, right, which is 2 volts, times the current through it, which is 1 milliamp, which makes the power dissipated by R2 2 milliwatts. Alright. Now R3, if I look at R3, it's got 6 volts, right? VF is 6 volts on one side, and it's got 2 volts on the other side, which means the voltage across it is 4 volts. And the current through that is 2 milliamps, right? So the power dissipated by R3 is going to be the difference of voltage across it, which is 4 volts, times the current through it, which is 2 milliamps. So that power is 8 milliwatts. And so then the answer to the question, do they dissipate the same power, would be no, they don't. Any questions? Yeah.
In the exam, do we have to draw those?
No, you never have to. I mean, I'm just trying to make it easy to see what I'm doing, but you don't have to draw the resistors like that. I just do it so that you can see where I'm getting my numbers from.
Yeah.
There will be a problem similar to this on the exam for sure. So hopefully this quiz makes sense to everybody. I mean, it might not be the same type of source. I don't remember what type of source I put on there. But it'll be one of the 4 sources and a similar setup where I ask you something about the power being dissipated, so make sure that it's clear how to determine the power being dissipated by a resistor. Any other specific questions about any quizzes or homeworks we've done, or any particular topic?
So on the exam, if we're calculating like the equivalent resistance of two parallel resistors, do you want us to show our work for that, or can we just say that these two resistors are in parallel and give you the number, or do you want the calculation written out?
So say you've got like a 2K and a 5K,
Uh-huh.
something like this, and they're in parallel for some reason.
Uh-huh.
If you just show that you did 2K parallel with 5K, that's how you write parallel, those little lines, and then you just do the calculation in your calculator,
Okay.
that's fine. I mean, I don't need to see all the work for it.
Okay.
So just maybe note that I mean, obviously, if I'm grading the exam, so I'll probably know that you did what you did when you did it. But it's just a good practice to show like, oh, I did 2K parallel 5K, and that gave me 1 point, I don't know, let's just say 1.2K. So that then I know that that's what you did. But also, if you draw this, and then in the next circuit you just draw this in its place, I'm going to know also that you found the parallel. So it's fine. Like, you don't have to be too careful about showing little minute things like that. I assume at this point you know what you're doing. Yeah.
Just a question, but if we do show the work and let's say we did the wrong calculation, but we show we know we do understand, like, let's say we do it, but then for some reason we pull the plus sign with the minus sign on our calculator and we get the wrong answer, could we possibly get partial credit showing like, hey, you at least understand that?
Yeah. I mean, I'm pretty reasonable. There was a lot of people on the mesh analysis problems and stuff that like messed up a plus or a minus somewhere, and I still gave them like 3 or 4 out of 5 because I know you knew what you were doing. It's just a stupid little mistake. Somebody got like 2 + 3 = 6. I know you know who you are. I'm not taking out. I don't think I took off a point. I know you know that it's not 6. Yeah, just if you guys are on the right track, obviously, and you make some minute mistake like that, I'm not going to destroy you. Did you have a question or no? Anybody have any questions about anything? Yes.
If you review over superposition and mesh, can you go over two examples of the homework?
Yeah. Do you have any particular homework that you remember it being difficult or no? Homework 6? 6C? This one? Is this asking for mesh? Yeah, I can go over this. Alright, let's go ahead and do that. Another useful study tip would be to just resolve the quizzes that you have. I know last time we talked about Baker's material and solving some of his practice problems. Maybe his midterm would be a good one to look at. The best thing you can do is just solve a bunch of problems because you just get really familiar with solving them and you get really fast, and that's how you do well on exams. Is by being fast at this stuff. One volt, 3 volts. And we're just trying to find VC, I guess, using mesh. Yeah. All right. Alright, so any particular way you want me to define the currents, or it doesn't matter?
I put it both up for the same.
So like this?
Yeah.
Alrighty. Okay, so I'll call this I1 and this I2. Right? And then I'll make my first mesh equation starting at the minus terminal of the voltage source and going this way. So when I go across this voltage source, right, I get plus 3 volts. And then I drop across the 1K, and that drop is going to be I1 times 1K. And then I drop across the 6K, but I have both currents flowing through that 6K in the same direction. So I add them, times 6K, 0. Okay, good there? Second equation, I'll start at the voltage source again, but this time we're dropping across the source, right? So that would be a minus 1 volt. And then I go across the 6K again, same thing. I'm going to add my two currents because they're going in the same direction. And then the 4K is just going to be minus I2 times 4K. Good there? Did you have any problems making the equations, or was it the algebra?
The algebra was determining when I should substitute I1 into I2.
So at this point, neither equation is particularly nicer to work with. So you would just have to pick one. So let's say I pick, I guess I'll just pick equation 1, and I'll expand it. So it'll be 3 volts minus I1 times 1K minus I1 times 6K minus I2 times 6K equals 0. And now I can group like terms. That's going to be a 7K now. Minus I2 times 6K. And now, at this point, I kind of just have to solve for I1 or I2. And then I'm going to have to plug it into the other one. Right? So, I'll just solve for I2, I guess, because it's easier. So it's going to be 3 volts minus I1 times 7K equals I2 times 6K. And then I divide both sides by 6K. I get 0.5 volts, or sorry, 0.5 milliamps, 3 volts over 6K, minus, and then what's 7 over 6, like 1.131, I don't know. Yeah, probably, you're probably right. 1.16667. So now I have I2, right? I have an equation for I2. And I can take that and I can substitute it into I2 in this other equation that I haven't touched yet. And then I'll end up with, and this equation will only be in terms of I1 at that point, and then you can solve for I1. So the thing with mesh is that when there's not a current source given to you, you end up with these two equations, two unknowns, and then you just have to do the algebra and it's all like, it's very free. You could have started with equation 2 and broken it down and plugged it back into equation 1. It doesn't matter how you solve it. There's no real convenient way to do it when you only have two voltage sources, or when you have two loop equations and neither of them look simpler than the other. It's all up to you how you want to solve it. You can go about it in any number of ways and reach the right answer.
Could you expand equation 2 and then plug I2 into it? Because usually whenever I expand equation 2 to like almost solve for I1 and then plug I2 into it, I never get the right answer.
So hold on, let me see if I understand what you're asking. Why is my brightness not turning up? Okay. So what I did was I took equation 1, I solved for I2, and now I'm going to plug that into equation 2. And you're asking, can you, what were you asking again?
Yeah, expand equation 2 and then plug I2 into it.
Like if I were to simplify this and then plug I2 in? Yeah, you can do that. So if I wanted to do that, I would go minus 1 volt minus I1 times 6K. Let me make sure I know what you're talking, if we're on the same page. And then a minus I2 times 4K equals 0. and then I get minus 1 volt minus I1 times 6K minus I2 times 10K equals 0. Now you would plug into I2, right? Or are you saying would you even go even further than this?
I would go further, yeah, usually.
And how far would you go?
Where I'd solve for I1.
So you would solve this equation for I1 and you'd solve this equation for I2, and then you try and do.
And then I'd plug them into each other.
I'm trying to think. So if I were to solve this, let me just see. I just want to see what happens. So if I were going to solve this for I1, I'd get minus 1 volt minus I2 times 10K. That whole thing would be over 6K, and that'd be equal to I1. And that would be negative 1/6, so minus 0.1667 milliamps. And then 10 over 6 is just, is that like 1 2/3?
Yeah, so that'd be 1.6667.
So now you got an equation for I1 and an equation for I2.
And then you can plug them in.
So if you plug this I2 right now in here, yeah, that will work. That will work. But then you can't go plug I1 back into the, you have to get, basically, you have two equations right now, but you still don't know what I1 is and you don't know what I2 is. But if you took this equation right now, this 0.5 milliamps, right, minus 1.167 I1, and you plugged it in right there for I2, you still have to solve this equation for I1 now, right? And if you did that, you would get some value for I1, some current value. And then you take that value and you plug it in here, now you get I2. You can do that. That should work. That sounds right. So if you've tried that and you've gotten stuck, my guess would be that you're either plugging something into itself and then it doesn't work out, or you just made a minor algebra mistake. So if you want to talk later or something about it, we can. But does anybody else have questions about mesh or anything I did here?
Can you do another mesh example with 3 loops?
With 3 loops? Yeah. Yeah, so let's go look at some of Baker's problems so that I don't use my own problems. No. There we go. Pick one of these that looks fun.
Let's go with 2A.
2A. Oh, this is an interesting one because it's got a current source shared between 2 nodes. I didn't give that on the exam, a current source shared between 2 nodes, because I don't think, we never did that, right? I never did anything like that because some interesting stuff happens. Let me just change markers again.
So should we do the other one that doesn't have the current source shared between 2 nodes?
Nope, not happening.
No, not today.
I have no idea what just happened. Yay.
And now there's wire back there.
You know what? Let me see. I have no clue. There's like a box down here, like a panel that I kicked, and I thought maybe that was it, but maybe not. Yeah, I think B would be a better bet because I didn't give anything like A on the midterm. Because there's some special things you have to do with that current source shared between the 2 nodes, right? Because you might be inclined to say, oh, then I2 and I3 are both 2 milliamps, and that's not true. So.
Wouldn't that just be your I3 being 2 milliamps? Or
So here, let me.
Split that 2 milliamps between I2 and I3. Wouldn't it?
Yeah, you have to kind of use KCL. So basically, let me just snip this. So you have a current that's over here, right? And that might be my I3. And this might be my I2. So you're going to make use of the fact that I2 plus I3 is 2 milliamps. Alright? But then when you do these loops, you have to still take into account that there is a voltage drop across that that current source. Okay? So it gets a little bit more complicated than the mesh that we've seen, so I don't think it's worth going into right now, because it might take me the next 25-30 minutes, and I'd rather cover as many useful things as possible right now. But if someone wants to see that at a later date, I can definitely cover it. Alright, so we're going to do B. I'll set it up. So B is going to suck algebraically because there's no current sources, but I'll still set it up for practice for everyone. This is no, this is not going to be fun for anyone to do with algebra. Oh, it's fall 21. Alright. Let's go back to the camera. Alright, so does it matter how I define the currents to you?
I would put them so your two loops are going in the same direction through the 1.5K, and then I'm not sure what I would do in the third loop. Yeah.
Alright, so let's do that. Let's go like this. And then that.
Yeah.
And then, yeah, the third loop is just not going to be friendly. So we'll just throw it that way. So it's going in the same direction as this one, right? But not this one. Alright. I'll call this I1, I2, and I3. So my first equation will be this loop, right? I'll start here basically, and I'll go across the voltage source. So that's going to be plus 1 volt, right? I'm going across this, and I'm going up by 1 volt. It's going to be plus 1 volt, and then when I get to this 1.5K, I'm dropping, and the currents are adding, right? So it's going to be I1 plus I2 times 1.5K, and then I get to this 1.5K, and the currents are also adding, right? So it would be I1 plus I3 times 1.5K equals 0, right?
All right.
Any questions about that equation? Alright. Second equation will be this loop. So here, right, I'm going across this voltage source, but it's rated negative, so that's going to be a negative 1 volt. Same thing when I get to this 1.5K, my currents add. And then now when I get to the 6K, I have I2, but it's being opposed by I3, so I have to subtract I3. And then I multiply by 6K, set equal to 0.
Okay.
Any questions with that one? Third equation is going to be the top loop. So when I go across this 2K, I drop by I3 times 2K. Then I go across this 6K, I drop by I3, and it's being opposed by I2. So I subtract. That's a big thing you guys need to keep track of, right? When I did equation 2, I was looking in terms of I2, so I subtract I3 from I2 in this term with the 6K. And when I'm doing I3, I flip them, basically. I'm subtracting I2 from I3 now, because whatever loop you're in, that's kind of what you're referencing. I'm saying the current here is I3, but I have to subtract I2. Where over here, the current here is I2, but I have to subtract I3, right? So make sure you keep track of those. And then when I get to the 1.5K, those currents add. So that's going to be I1 plus I3 times 1.5K equals 0. And you can only imagine that this isn't going to be fun to do the algebra for. If I were to give you a 3-loop mesh ever, I would always give you a current source so that you don't have to do this. 3 equations, 3 unknowns, because it's just no fun. Did you have any questions about this?
No.
All good?
Yeah.
All right, cool. Anything else in particular? Yeah.
So if there is a
Oh,
3-loop mesh on the exam, you'll give us a current source for one of the loops?
That's right.
Okay.
Yeah.
Sorry, I didn't mean to interrupt.
What was your question?
Wasn't it over Thevenin with 2 voltage sources?
Yeah, I can. Thevenin with 2 voltage sources. So, was there a particular homework problem that I...
Yeah, 1A, homework 8, yeah.
This?
Yeah, because for that one, I kind of solved for the Morton and then just use voltage transformation.
Yeah, you can do that.
But like, I just want to know how to do it with like Norton and Thevenin first.
All right, cool. I'll do this one. I'll do this one, and I'll slightly modify it. Do you want me to do this exact problem, or do you want like a variation of it?
Just the exact is fine.
All right. So this is homework 8-1A. Three, okay, 6K, 3K. All right. So, I guess the first thing I wanted you to find was probably VA. Is that right? Did you have any problems finding VA initially?
No.
What was it, -6? I think so. All right, so I'm not going to waste time with that then. So you want to know how to find the Thevenin voltage? Is that basically the
Yeah.
problem? All right, so if I'm finding the Thevenin voltage, the first thing I'm going to do is get rid of the load, right?
Yeah.
I get rid of my load resistor. So this is -12 volts, 3K. Now I got no load there. Alright, and then this is 3K, and this is 9K. So what I'm trying to find is the voltage between those 2 points, and that gives me my Thevenin voltage, right?
Yeah.
Okay. What's the voltage here? And what about here? Okay. So we need to find the voltage here, right? Which means we need to find the drop across one of these resistors, and we don't know it because we don't know the current. But we can find the current, because if I just draw this out, would you agree that these two resistors are in series?
Yeah.
Okay, so I can go negative 12 volts, 12K, 3 volts, and now I can find the current that flows through this resistor by 3 volts minus negative 12 volts over 12K. That'll give me I. And that's going to be 15 volts over 12K, which is going to be 1.25 milliamps. Alright, now that I have I can find the drop across these resistors, and then I can find this voltage, which gives me the Thevenin voltage, right? So if I take 1.25 milliamps times 9K, I think it's like 11.25. Let me multiply just to make sure. Yeah, 11.25. So that means that the drop across that 9K is 11.25 volts. And so then 3 minus 11.25 gives me my voltage right here, which is going to be negative 8.25 volts, and that's going to be my Thevenin voltage. So yeah, exactly, it would. So let's do it the other way too, just to prove it. I'll use another color. So that drop, right, that drop's going to be 1.25 milliamps times 3K, right, which is going to be 3.75. So if I take negative 12 and I add 3.75, I get negative 8.25, right?
Yeah.
So either way you choose to do it, you get this for your Thevenin voltage. Do you have problems with the current, or sorry, the Thevenin resistance, or it was just the voltage? Just the voltage. Anybody have any questions about that? Yeah.
In this case, could you also say that, like, the total drop between the two of them is 15, and since 9 is, like, 3/4 of the total, like, resistance, you could just say, like, 3/4 of the drop across the entire thing would be that.
Yeah, that's right. Yeah, it's basically a voltage divider, except instead of having, you know, the standard voltage divider where we have it look something like this, where this is ground and this is ground, it's a voltage divider where this is like, there's two different, you know, it's the same principle. So yeah, exactly like you said. One sec.
Say, theoretically, if for some reason I had an issue finding the Thevenin resistance doing a problem like this on the test, if I were to work backwards, because I know what VA is supposed to be and I know what the Thevenin voltage is, and then solve for the resistance, could I do that way as well?
No, just because VA is meant to check your work. It shouldn't be used as like a crutch to help you find the other stuff, because in real circuits, right, in real life, when people do Thevenin and Norton, the circuit might not have a load connected in the first place, so they don't know what this voltage is going to be. I just give you that so that you have something to check yourself with.
All right.
So I wouldn't use it as a method to help yourself solve the problem. You could use it. No, I was going to say you could use it to help check yourself, but now I'm just repeating myself. Yeah, so basically use the methods that we know for Thevenin, Norton, current, and voltage, and then if you get stuck, I guess.
I don't think I will. I was just asking.
Yeah, I wouldn't want you to use that as like a helping hand. Yeah.
Would you mind
Yeah, no problem. So when we find the resistance, we have to basically short, right, across the two batteries. So they basically are gone, right? And we look, and then my load is gone too. So we look, if I send a current in this node, right, how much resistance does it have to go through to get to the other, the other load terminal? And it has to go through this 3K, right? And then it also would have to go through this 9K. Okay, let me redraw the circuit now because it's just an absolute disaster. So it would be a 3K here, my load terminal, 9K, and then my other load terminal, and then this is ground. So my current, right, would have to go in and it would split into these two paths, right? So that's basically a current divider, and my 3K and my 9K are connected in parallel. Do you see that they're connected in parallel? Okay, so my Thevenin resistance is 3K in parallel with 9K, or 3K times 9K over 3K plus 9K, and I don't remember what it is. I think it's 2 point something. 2.25K. All right. Any questions about that? No?
What was the quick conversion to finally
The current?
current?
So it's using Ohm's law, right? I equals V over R. So if I just take my I Norton is equal to basically my Thevenin voltage over my Thevenin resistance. So in this case it's negative 8.25 volts over 2.25K. So whatever that is, that's going to be my Norton current. Alright? And that's using source transformation. Blech. Ran out of room. Alright. Any other questions about anything? Yes.
Can you go over exactly what source transformation is? It's so big to use on computers. Is it just using like Ohm's law to state that in this circuit, something similar to this one, it's the same thing? Or?
It's using Ohm's law to literally replace replace a voltage source in series with a resistor. Like if that combination of components is in a circuit,
Right.
you can replace it with a current source in parallel with the transistor or resistor, and it will give you the exact same circuit. It doesn't affect the circuit at all. It's basically an equivalent circuit. But
Oh, so source transformation is just essentially saying it's saying well, since you can have a current divider and a voltage divider, you can flip the two of them and then still have the same outcome.
exactly, yeah. So if I have, I had some room on this page, so let me just do it over here. So let's say I have some circuit. I don't know what this circuit is. This could be any number of components. And over here, I connect my voltage source and my series resistor to that circuit. I could take that V and R and I can use Ohm's law, right, to get an equivalent current source with the same R and plug that into the circuit, and that will give me, it will change absolutely nothing about how the circuit behaves.
Okay.
That's basically what it's saying.
No, that makes sense. I was just getting confused.
So it's used usually in Thevenin and Norton, but you can also use it in other circuits where, if, for example, I think I gave this example already, but I'll give it again. So say I had a circuit that looked like this. you could take this little piece of circuitry completely out and replace it with a voltage, the series resistor, and then connect it over here, and now you just have a really simple single loop voltage divider, right? If you were trying to say find that voltage, it would be easier to do it in this circuit than it would in this circuit.
Right.
So that's another place where it could be used. I've seen the most useful application of it when doing Thevenin and Norton, so that you can avoid solving for one of the three variables. But it can be used to help you solve other problems too. I think the thing is in this class, none of these circuits are complicated enough that you would feel inclined to do a source transformation just to help you solve it, because you might just, if you saw this, you'd already be like, oh, I can combine those in series, and then it's just a current divider. Like, there's no real reason to.
There's not really an use it.
There's not really a benefit. Yeah.
Are there going to be any questions on the exam that are specifically about source transformation?
No.
Will there be any opportunities to utilize source transformation in any of the problems?
You can use it in the Thevenin and Norton problem,
Okay, that's super.
but there's no like dedicated problem where I'm asking you to use source transformation. I also didn't put any problems on there where like I was like, ooh, I hope they use source transformation, or noticed that they could use source transformation here.
Okay.
But yeah, for the Thevenin and Norton one, it would be beneficial to save you time rather than finding the third metric, right? Okay, so that's... Alright, so what have we gone over? We've gone over Thevenin and Norton, source transformation, some mesh, some dependent sources, some power. This is a mess. Any other questions about any topics? Or does anybody remember any quizzes or anything that you thought were difficult? I feel like we've probably covered pretty much everything on this list now.
Are you going to have the office hours after or no?
I mean, I'm going back up to my office, so if people need to come up there for stuff, you can come up with me. But I don't technically have office hours. So let me make this I've been actually meaning to make this clear to everybody, and I keep forgetting. I know that a lot of you are probably fresh students, and you don't know, like, this is probably one of your first semesters with like in-person classes. Office hours are not the hours when I'm in my office. They are the hours that are dedicated for you to come to my office. I'm in my office all the time, but that hour is dedicated for you to come. So I keep having people email me, right, and ask, can I come to your office hours? And the answer is yes every single time, because that's what it's for. So in general, it's not good to email your professors and ask if you can come to their office hours, because their office hours are set aside for you to come. So for those of you who have been emailing me asking if you can come, I always say yes, but just know that you don't even have to ask. Like that they're there for you to come, so if you come, I will be there. I'm there other times too, and if you want to come outside my office hours, obviously then you have to ask. But office hours are dedicated time for you to come. So don't feel like you need to email me to ask like permission to come to my office hours, because I'm there waiting for you to come. All right?
I seem to recall for makeup quizzes, though, that I think there was somewhere on the website or something like that, you asked for us to email you about our makeup quizzes when we come to your office hours. So I think that's why people might be emailing you.
Oh, did I tell you guys to email me?
I think that was the case, but I might be
Well,
misremembering.
you said email you for access to your office, because
Oh yeah,
up to the elevator.
I wasn't. They didn't, because in the past they didn't have that sign down there where people can call and get up, and I don't even know how well that works. Does somebody answer the? How many people of you have called that?
You call,
that
somebody
number?
comes down from like the second or third floor,
And they let you up?
and bring you up.
Oh, that's a pain. Okay. Yeah, I mean, I don't have a problem with you emailing me saying, hey, I'm at your office hours. But people like, hey, can I come to your office hours? I just wanted to let you know that the answer is always yes. Unless it's outside of my allotted office hours time, because then I may or may not be there. I will certainly be there during that hour. And that's why I'm there, is for you and to answer questions and for you to make up quizzes. But maybe I did say something about emailing me.
I think I was misremembering because I'm reading it now. It doesn't look like it.
Yeah, just so that, because I've had professors go off on me before for emailing them and asking if I can come to their office hours, because they're like, that's what it's for. Like, what do you think it's for? So just so you know, so that doesn't happen to you.
Man.
What?
You're like, I don't know, man.
I mean, I didn't know. I thought that when I was a freshman, I thought that office hours were the hours they were in their office.
Yeah.
Right? That's what it sounds like. It didn't make sense to me why. Yeah, whatever. Just so you know, office hours are universally known to be for students to show up. So I'm in my office, it's probably 7 hours a day, but I have one office hour where I'm waiting for people to actually come, and I'm setting everything else aside for that hour. So, all right. It looks like we went over everything on the list. I can just check a bunch of this stuff off. Unless there's is there any particular topic on here that bothers everybody more than anything? Yeah? A superposition example?
Yeah, that's
Any particular one?
one with the current source and volt.
Okay. Let's go to Baker. Just pick a random semester. Homeworks. Let's do like 6.
I think we have another question order.
Yeah?
Could you do the one on this midterm?
On Baker's midterm?
For last semester? And this question too.
This one?
No. Not that one. I think it might be the one of us. Or maybe before.
It's one of them.
This one? Yeah, let's do it. What if I said I couldn't do it?
I'd call you out.
Would you renounce your giving me of the shirt?
Yeah.
All right. Well, I think I can do it. I need more colors. I'm getting bored of these. Wow, this one sucks. I kind of like it. Never mind. All right, 2.5 volts, 2K. I saw that he gave a really interesting problem 6 on one of these midterms. It's not this one. That would be an interesting one to look at afterwards. It was from my semester. Alright, so we're trying to find Vx. Alright. Okay, so do you want me to get rid of the voltage source or the current source first? The current source? Alright. So when I get rid of the current source, I'm going to open it, right? So that's going to look like this. I'm trying to find Vx. Alright, so the thing to notice here, alright, so Vx is equal to Vx1 plus Vx2. The thing to notice here is that no current will flow through that 1K, right? which makes this entire circuit just a voltage divider with 2K, 2K. So VX1 is going to be 2.5 volts, right? This is 2.5 volts times 2K over 4K, or 1.25 volts. Any questions about that? No? All right, so that's with no current source, and now with no voltage source. We're going to get a short over here. Okay, so we know I have 2 milliamps flowing right here, and then the resistance in both paths is equal. So that's just going to split in half, which means 1 milliamp is going to flow there, and 1 milliamp is going to flow there.
That's only because they're in parallel.
That's only because they're in parallel, but it's also, you mean that they split, or that
No,
they are
not
equal?
actually that they're, or I guess technically neither is because they're in parallel, but they are.
They are in parallel, that's true. The reason they're equal is because the resistances are equal. Okay? So if they weren't equal, I'd have to do a current divider, or I could do a number of other things, but I would probably just do the current divider. But basically now I know that I have 1 milliamp through this 2K, which means I know that the drop across it is going to be 2 volts, which makes VX2. I'll just write it out. 1 milliamp times 2K gives me 2 volts. All right, so that makes VX, the original VX. What? Huh? Did I do something wrong?
No,
No,
you're good.
no.
No, he's in the middle because, you know, it's 0 volts.
Oh, was somebody wondering? Is anybody confused why? Oh, wait. I just want to find out who was asking the question first of all, and what was your question?
Oh, I was not questioning like, I think you mix those two, but I see that you use 1 amp instead of combining those two and then doing it.
Oh, yeah. No, once right here, right. All I need to know is this. That's all I need is that little blip right there, because I know this is ground. I know that VX2 is just going to be the drop across this resistor, right? And I know I have 1 milliamp flowing through there. That times 2K gives me 2 volts. All right. So then my VX total is whatever, 1.25 volts plus 2 volts, or 3.25 volts. Yeah.
Couldn't you also just know, since there's 2 amps flowing over the 1K, since there's 2 amps flowing over the 1K, you can also just get 2 volts from there, saying it's a 1K increase from where the current source is to the volt you're trying to find?
No, because you don't know what the VX2 is. So you know the
Well,
difference.
wouldn't that just be 0? Because
Are you referring to this node?
yes,
That's not 0.
it's not 0.
No, that's going to be 4 volts.
Oh, interesting.
Because that's 2. If this is 2 volts and I have 2 milliamps flowing through this 1K, that means I have a drop of 2 volts across here, which makes this 4 volts.
Okay, that makes sense. Yeah, I was confused for a second.
So yeah, make sure that's something that we definitely need to, keep in mind. Current sources have a drop right across them, but it's not intuitive to look at and find out. You have to use Ohm's law with all the resistors to figure it out, right? But you can base it off of the fact that this was 0 volts, and I could take the drop across this resistor or the drop across that resistor to get this voltage, right? Either or.
So with that one, I could have also combined the two 2Ks in parallel, solved for my total voltage, and then done a voltage divider, right?
Yeah, so if you take the two 2Ks in parallel, what would you get?
That would be 1K.
And then you have 2 milliamps going through that 1K, right?
Uh-huh.
And that would give me
2
2
Yeah.
volts, right? So that's exactly the same thing. So that would work.
I like voltage dividers better.
Yeah, me too. All right. Any questions about that one? Okay. Any questions about anything else in particular? Did anybody else do any other Baker problems and find them hard? No.
They do be having decimals on that.
Yeah, I try to avoid that because I hate that. That's all unnecessary. I mean, it's unnecessary when you're doing hand calcs. In the real world, everything has decimals, right? But like I was doing we were doing some laser optics project, and we needed a 57.35 ohm resistor. Like exactly. Like if it wasn't that, it would have thrown the oscillations off or something. And it's like an insanely expensive resistor because to get it that precise is like ridiculous. In that case, obviously, you need to.
I mean, don't most resistors have like a fluctuation of like 5%?
Yeah, there's like really cheap resistors that have they call it tolerance of like 5%, but you can get resistors that have like really, really low tolerance and they're really expensive.
How expensive are we talking for one resistor?
$30?
Let's see. I don't know. I've never bought one. Anybody used DigiKey before?
I have.
This is like the #1 supplier for electronics parts, so you'll probably use it sometime before you graduate. All right, so let's look at chip resistors, the one that we usually go with, and then see how it says tolerance. So here's like the least tolerant ones. This is 0%.
To -10%.
I don't even know what the negative means.
Yeah, I like
We're so good.
it. Negative tolerance. It makes it.
Okay, so for example, this is $24 for one resistor, and just to put that in perspective, normal resistors are like less than a penny.
Yeah.
Yeah.
So this is thousands of times.
100 for like $5.
What's that?
If you get like a pack of 100 resistors for like $5.
You get a pack of like
You can get
tens of thousands of resistors for $5. Like resistors are incredibly cheap. So for a resistor to cost $24 is outrageous. I mean, if you just think about a product, right? Something that has electronics inside of it, there's probably dozens of resistors in there. If you had one resistor in there that was $24, the product's price would go through the roof. So yeah, that's an example. Plus or minus 0.01%. So if this is 10K, that means it's probably accurate to like 9,999 ohms, right? It probably doesn't vary by more than 1 ohm, which may be useful in some applications, but very rarely will you need anything that good. I wanted to look at that interesting one from my class.
So what did you do on that project where you needed the super precise resistance? Did you just combine some in parallel?
No, my boss bought it. He spent the money on it. He needed it because in laser optics and things, and this is like industry stuff. This isn't like a school project. He needs to meet specs, or the people that are buying his stuff won't buy his stuff. So he just spends the extra money and then charges them more according. He's like, well, you want to meet this spec, then you need to pay me an extra $24 for this resistor.
That's also important for people that care about them.
Yeah. What am I looking at? Where's my class? Oh, right here. I think it was the midterm. Problem 6. Yes.
You remember that? Oh, let's go.
All right. So let's solve this one because I think it's fun. This is. I don't remember it. For whoever asked how I remember it, I was looking through my midterm the other day just out of curiosity, and I saw this problem, and I thought it was interesting.
I thought it was living rent free in your head the past 5 years.
No. No, I got 100 on this midterm.
Let's go.
I hope you all get hundreds on my midterm.
So do you have nightmares about problems like this? Or?
Not this. I don't think this one's. I think this is a cool problem. I think it's an interesting application of the dependent sources. So as a gain of 3, no, you don't even. I don't think you even need to use mesh. So that the question is find Vx. So note that he's got Vs connected right here and Vx connected right here. So he's basically he's saying whatever Vs is, that's what I want to be the plus of this dependent source, and whatever Vx is, that's what I want to be the minus of this dependent source, right? So here's the thing.
Yeah, if you're
Oh, sorry guys. Thanks. All right. So, okay, I don't even remember what I said.
Oh, there's 2 VSs.
There's not 2 VSs. That VS
One is
is the
red.
same as this VS. It's just saying it's connected without a wire, basically. It's saying whatever VS is, that's going to be the plus input of my dependent source, and whatever VX is, that's going to be the minus input, right?
Cool. Just like this place, okay.
Yeah, exactly. So, you would think, right, you need Vs and Vx in order to solve this problem, but you would also think you need to know what this source is in order to solve for Vs and Vx, right? Doesn't that seem
Kind of.
like it's kind of like Vs and Vx are dependent on this source, but this source is also dependent on Vs and Vx. So do you see that? But what I think I noticed when I solved this problem, and what he hoped we noticed, is that you know the current flowing through this resistor, right? So you know that the drop across that is going to be 9 volts, right? So no matter what Vs is and no matter what Vx is, the difference between them is 9 volts. And that's all that this cares about, is the difference between them, right? So that difference is 9 volts, which means that this is a 27 volt source, right? Because the gain is 3. So that means that Vx is equal to Vb plus 27 volts, right? So I guess now, and then we know that Vx over 9k. Yeah, I guess now you have to do some KCL, because we know that current, we don't know this current. Well, that current is 0 minus Vb over 9k plus Vs minus Vx over 9k. Oh, sorry, I don't even need that. That's 1 milliamp. And that's going to be equal to Vx over 9k. All right, and then now we have an equation in terms of Vb and Vx, right? And then we also have this equation in terms of Vb and Vx. So those are my 2 equations, 2 unknowns, and you could solve for Vx using those 2 equations. I just thought it was interesting how it looks like it's almost impossible to solve, but it's not impossible to solve.
Well, I mean, that just means you have to really understand what those 2 things represent.
Yeah, no, I mean, I could see where freshman me would have been like, how the hell is this possible? And how any number of students could have been like, how the hell is this possible? And I couldn't find it on any of his other midterms, so I assume it didn't go very well. And he probably removed it.
Let me not do that again.
Yeah, all right, well, it looks like we're pretty much out of time. So if anybody doesn't have any other last-minute questions.
Shirt.
Oh, my shirt. Yeah.
The shirt.
Do I have to open it on camera?
Yes.
You can if you want.
Oh my gosh, are you guys joking me? Mesh analysis is just spicy KVL. Should I wear this for the midterm?
Yes.
All right, I'll do it.